Hi, Jason, and everyone say it. Hi, Jason and Justin. We hope you're watching this video and that you're doing great at anyway, so this one here, this is number 66 from section 5-4, and trying to teach you how to graph something by hand. So if you have something like this, this is the B, or the frequency, they call it in the book omega, W. So to find the period, it's 2 pi divided by omega, or B, which I like to call it, okay? So in this case, that period is 2 pi over 2 pi, which is 1, okay? Now this one doesn't have a phase shift. This one just has, let's say, but it does have a vertical shift, right? So probably what you want to do is make a line down here that it's going to shift down around. So this would be that line. I should put arrows on the end. So this is the line y equals -2 because it shifted down by a factor -2, right? And then cosine starts, so what you kind of do is you pretend that it's starting up here, except instead of starting up here, it's starting down here, and it's cosine. And cosine usually starts at the top and goes down the bottom, but because I have a negative cosine, it's going to start below this line and then head up and then down. You understand that? Hello? And it's going to take the period is 1 radian, okay, which is not very many radians, right? So this is a pretty quick moving function, okay? Because a normal cosine function takes 2 pi radians to complete 1 cycle. This one is taking 1 radian. So this one's going like 6 times as fast, 6.28 times as fast as a regular, so it'd be a squish factor of 6.28. But I'm going to stretch that on my scale, so I'm going to end up calling this 1. You can scale your axes however you want, right? And then it's going to go start down. So where is this thing going to start? If it shifted down to, and this is an amplitude of -5. -7. Do you guys understand why that start point is -7? Okay? Because it shifted down 2, and instead of starting up here at 5, it's flipped, so it would start down here at -5, but then it's moved down 2 from there. So it's going down there. And then what I would do is find the end point, which is over here. So this point is going to be the point 1, comma, -7. And then I would find the halfway point, right? Well, the halfway point is going to go from -7, and it's going to go up 5 units to y equals 2, and then it's going to go up 5 more units to where? What's this point going to be right up here? 3, right? Because if this is, my scale is at 1, 2, 3, 4, 5, 6, again, an arbitrary slope, okay? But it's going to go up 5 from here to here, and then up another 5 to get to here. And then to find these points, it's going to cross the axes here. So a cosine function crosses this midline, I call it, okay? Y equals -2. And it's going to do that at the quarter points. So this would be the point, what's halfway between 0 and 1? 1/2. So this is the point 1/2, comma 3, right? And this would be the point 1/4, comma -2, right? And this over here would be the point what? 3/4, comma -2. So when they say graph using the 5 key points, that's what they mean. So cosine function kind of starts this way goes through that point up to here. Comes down kind of curvy-ish, and then kind of curves back this way. And then that's one period or one cycle of that function, right? And then it would continue on forever after that, right? But so it doesn't just stop there; it keeps going forever, right? Does that help? Good? Yeah. You can't take the World Series serious, but the LA Dodgers did. Thank you. Okay. We have to handle that. Okay. So anyway, this one has to do with phase shifting. So in the last section, we talked about changing the amplitude, which is this letter, and the frequency, which is this letter. And now we're going to deal a little bit more with this thing, which you kind of did on that map that I gave you guys. And this is called the phase shift. And this is the vertical shift. Okay? And in your book, they have it in a different format. Okay? So they have y equals a omega. This omega is exactly the same as my b. It's the same number. But what they do is they distribute this b through the parentheses. So this symbol phi is actually b times c. And the reason they do that, I'm not exactly sure because it makes it harder to graph it by hand, but it makes it easier to plug it into your calculator because you only have to use one set of parentheses here instead of using one set then another one like this. So this is the way it will appear in your book. To make this form into this form, all you have to do is take this number phi, which is this circle with a little slash through it vertically, and divide it by the frequency, and you will get the phase shift, which is c over here. Okay. So for instance, over here, well, we'll do it with this problem down here and also. The amplitude is always positive. So if the amplitude is negative, what happens? What? Oh. Right, undo that. Is that better? It still looks kind of blurry, doesn't it? Oh well. So anyway, what?
When you were recording for 3 hours.
Yeah, I did that. So anyway, these are some of the steps when you're graphing these by hand. Because you will have to determine the amplitude and period, which we kind of talked about in the last time. Determine the starting point. Determine the end point, which is equal to the start point plus one cycle. In other words, you add the period to the start point. Divide the interval into 4 subintervals and so on and so forth, and then plot the points and sketch the function sketching it in both directions. So let's try to do that with this one right here. All right. So, and I did it for you, but we're going to do it separately. So can I shrink this thing? Let's get rid of this. Let's make this smaller. Why is it 100? Oh, it's way too big. Let's make this smaller. And then I can put it on my screen. So I'm going to grab this somehow. Partial. So I'm going to grab this and put it on a separate sheet. Okay. So now we have this function. You guys can tell me what the amplitude. What's the amplitude? 3. Okay. Now the period. This is b. Okay. Very good, Maddie. What did you say? It's pi because this is b, which is equal to omega. Okay. And the period is 2 pi divided by b. Okay. So it's just 2 pi over 2, which is pi. Okay, so this function is going to repeat itself every pi radian. So basically it's going twice as fast as a regular sine function. Okay? Now we got to figure out the phase shift. So just by looking at this, this won't give you your phase shift. Okay? So what you do is you go omega, or b divided by, b divided by omega, right? Phi, which is this thing, divided by omega, which is this thing. And you get that the phase shift is pi over 2. Okay, so if I wanted to write this in my form, which I kind of like better, and is in a lot of books that way, it would just be a equals 3 sine of 2 times x minus pi over 2. Okay, you see that if I multiply by this, I get this. So all they do in your book is they take this 2 and they distribute it through, because it does make it easier to put into the calculator. Okay. Now I have to figure out the start point. Right, so I'm going to kind of draw an axis, and we have a phase shift of pi over 2. And so I'm going to just kind of start, draw my axis in here. Shouldn't be dotted, but that's okay. So I'm going to call this point right here pi over 2 comma what? Hello? 0, right? There's no up or down shift. Done? Now I'm going to find an endpoint. And this is why I don't really like to scale things too much. You have to add 1 period. So it's going to take pi radians. So if I take pi over 2 and add pi to it, so the start point is pi over 2 comma 0. And the endpoint, I need to add pi to that. And however you want to think about that is up to you. You can find a common denominator. So you can think of it as it's pi over 2 plus pi, which is, how many pi's over 2? 3, that's 3 pi, yeah, it's 3 pi over 2. Guys, it takes 1 pi to go from the beginning to the end of this cycle, right? So this point is going to be 3 pi over 2 comma 0. And then you have to find the middle, which is also going to be something 0. And so you have to figure out what's halfway between pi over 2 and 3 pi over 2. What is it? Pi. How do you get that, Olivia? She just thought it was right. Well, there's a bunch of different ways to do it. But you think 1 whole cycle is pi, right? So you add a half of a pi to it. So pi over 2 plus half a pi puts you at pi comma 0, right? Or if you wanted to do that algebraically, you would say pi over 2 plus 3 pi over 2 and divide by 2, okay? So it's like the midpoint. So those are 3 points. And then you know, because it's a sine, it starts at 0 and it goes up, and then it comes down. And now all I have to do is figure out what these points are. Well, how high up of endpoint is 3 pi over 2 comma 0. And the midpoint is pi comma 0. And the quarter points, not pi over pi comma 0. And the quarter points are 1/2 of the way between here and here. So who can tell me what's halfway between pi over 2 and pi? Go again. It's not pi fourths, because pi fourths is over here, right? 3 pi over 4. Very good. 3 pi over 4 what? 3, because the amplitude is 3, right? So this point over here is 3 pi fourths over 3. So you can think, okay, it's 1 pi, right? So each quarter is going to be a quarter pi away from that. Or you can take this plus this and divide by 2, which algebraically becomes a little bit complicated. 1/2 plus 1 divided by 2 is 3/4, but however you want to do it. And then down here I have what? 5/4, very good. You guys are too smart. 5 pi, let me erase this because this is down here I have, let's try to make it to scale. Down here I have 5/4, 5 pi over 4, what? -3. And then I can sketch one period of my graph. So I'm going to try to do this as best as I can on my home board. I'm not very good. Not, but you're kind of curve. That's better. This is hard. We should have a sine function, right? And it goes on forever, okay? It doesn't go up forever. It keeps going like this, right? Forever and ever and ever. Okay, so good. Oh. And so the part we just sketched is this part, right? I should do that in a different color. How about in green? Okay, so you get the idea, right? How's that? Good. So there's one complete cycle. Any? Okay, we're recording again, so pay attention, everyone out there. Word problem. According to the Old Farmer's Almanac, the number of hours of sunlight in Boston on the summer solstice, that means the longest day of the year, is 15.283, and the number of hours of sunlight on the winter solstice, that's the shortest day of the year, what is it, December 21st or something like that, is 9.06. So this would be, what's the longest day, June 21st? That seems all right. June something. Find a sinusoidal function of this form that fits the data. Okay, so this is a really nice problem. You will have one like this, and people complain about these, but they're good for you. Okay, so at what point? At the point where they show you, oh, here it is. Because they show you some real life stuff that's going on. Okay. No one what? Oh, yes they do. Guys, who does these problems? The guys the farmers. They want to figure out when to plant their crops. And they want to figure out to predict the number of hours of daylight, so they want to know whether they'll be able to farm on those days. Okay? Hey, okay. I'm going to tell you a story again. Okay? You wanted my story. Back when I was in college, I used to go home to New York and lifeguard on the beaches in New York.
Oh, so you're part Baywatch?
What? I was Baywatch, yeah, except it was like inner city New York, drowning inner city kids. And the reason they drowned, and the reason I bring this up is because it has to do with sine and cosine functions. Because because you guys live out here, you don't know about tides, right? But on the coasts, you have ocean tide. And at low tide, what happens is the height of the ocean is based on the cycles of the moon. And they're basically 30-day cycles. And except that there's daily high tides and low tides. I'm not exactly sure how the moon has something to do with it. But the tide goes in, the tide comes out, and based on those cycles, you can make a sine wave modeling the high and low tide. So when I was a lifeguard on the beaches in New York, like off Long Island, these kids would come from the city, and we had little rafts that they could go out and bob out to at low tide, right? So they go out at low tide, and then they'd go to these rafts and they'd hang out because they couldn't really swim, right? So they kind of bob up to their necks and they kind of get out there, and then they climb on the raft and they'd sit out in the sun on the rafts all day. And then the tide would come in and the rafts would go up, and now when they tried to swim back, it was like 4 feet over their head. Right? Because there's low tide, high tide. That's how ships get stuck a lot. They go somewhere there they shouldn't at low tide, and they get shipwrecked. And so anyway, these guys would try to bob in off the raft, and then they realized that it was over their head, and then they start drowning. And that's where I came in. Okay, so Baywatch, no he didn't. I had a little rowboat, and I would row around and I'd pull in drowning inner city kids, left and right, like sometimes 3 times a day, who didn't know about high and low tide. So if they only knew their trigonometry, they could have predicted when their high and low tides would have been, and they wouldn't have but really though, but really that's what, captains of ships and stuff like that, they have to know, how those cycles work. So anyway, what is happening here, this is similar thing, except it has to do with hours of sunlight and daylight. So what I would do is kind of draw a picture of what's going on, okay? So at some point in June, you have a lot of hours of daylight, and then at some point in December, you have lower hours of daylight, and this goes on from year to year. So this would be, like from here to here, would be how long? That would be 1 year, or 365 days, okay? So you call that 365. Okay, and even though it's in days, you can make that be radians, all right? Okay, so it's 365 from here to here. And what? Well, it's easier to model as a cosine function than as a sine function, because then you're going from top to top instead of starting in the middle. See, you could model that as a sine function, but then you'd have to shift it a quarter of a period. You know what I'm saying? Okay? So, the way I would do this first is find the amplitude. Okay? And the amplitude is the high point, which is 15.283 plus the minus the low point, which is 9.067. And I had all these numbers worked out, but I seem to have lost my calculations. Divided by 2. So could someone punch that on a calculator for me real quick? What do I get? 15.283. What is it? 3.108. 3.108. So we'll call that 3.11. Why do you divide by 2? Because it's the top minus the bottom. That's the distance from here to here, right? And then if I divide that by 2, because the amplitude is the distance from from the midline, right? So if I were to do a line going straight across there like this, which I'm going to do next anyway, okay? The amplitude is the distance from here to here, okay? So that distance is 3.11. With me? Okay? Now I got to figure out the shift, the D value, right? The vertical shift. So it's shifted up, right? And the way I get that is by taking the average of these max plus the min, the max and the min. So I'm going to go 15.283 plus 9.067, and I'm going to divide that by 2. And what do I get? They actually use little b. No, it's, thank you, 12 point, we'll just call it 12.1. It should be pretty accurate. 75. Okay? So that's D. So I'm looking for something in this equation. So what I'm looking for is, I'm going to start off with this equation. Y equals A, and we're going to model it with a cosine. B X minus C plus D. So far, I know A, and I know B, and B is pretty easy, because what's that? It's 2 pi divided by 365, right? Because it's the 2 pi divided by the period, which is 365 days. So now I know this. And the phase shift is when it, so a normal cosine function would start at 0, right? Which would be January 1st. Yeah? So you have to figure out how many days after January 1st, well, I guess it's exactly half, right? That, here's the function. So this would be June 21st, which is half of 365. Let's just pretend that that's the 183rd day. Okay? Okay, so you understand where I got that from? Does that make sense? Wait a minute. Let me think. We determined by adding up all the days before June 21st, which is summer solstice, that there's 172 days. It doesn't start, the longest day of the year, or the shortest day of the year, isn't at January 1st, it's December. So the summer solstice is the 172nd day of the year, right? So that's your horizontal shift. What? Yeah. Oh, I would tell you, like on the 100,
Okay, yeah.
the longest day of the year is on the 170. Yeah, I would tell you. Okay. So now we can plug all this stuff into the equation, except what I'd like to do to make, they want it in this form. Okay. So Wx is b times this. So I'm going to take omega x, omega, well, I can't see what I have. Omega is, and phi is this times this, okay? So the way I write this in an equation is y equals a, which we determined, which is 3.11. We're going to model this as a cosine function. Cosine. And then we're going to plug in our b, which is, you can leave it just as 2 pi over 365 minus, so this is b times, so this b, okay, is going to be b times c, okay? So you have to do that on a calculator. Can anyone do that? 2.96, is that what you got? You took 2 pi, you multiplied that by 172, and divided by 365. So this is 2.96?
Yeah.
Thank you. Oh, I forgot something. I forgot a variable, okay? Minus 2.96 plus 12.175, right? And now I'm going to take all that mess and I'm going to try to plug that into my graphing calculator. Good? Yeah, so let's see if we can do that. We're going to pause for the studio audience here. Start recording. Now I'm going to try to plug all this into my graphing calculator. First of all, you got to make sure you're in mode radian, okay? Then I'm going to go back to y equals. I'm going to plug in 3.11 cosine, and then you got to be a little careful, right? 2 pi, I'm going to put in parentheses, right? 2 pi over 365. 2 seconds, is this pi right there? Pi divided by 365, close that parentheses, minus 2.96. What? Hold on. Close that parentheses, plus 12.75. Okay? Now, before I graph this, hold on. What? Oh, 12.175. Sorry. 12.175. Okay? Before I grab this, I want to set up a window that makes sense. Okay? Maybe for about 2 years. Okay? So how long would 2 years be? 720 days. Okay? So I'm going to set this to 720 days. Okay? So this is where I make sure that things kind of make sense. My y-min, since I never get negative solstice days, I'm going to just set that to 0. And the longest day of the year was how long? 15. So I'm going to set that to like 20. Okay? And now I'm going to cross my fingers and hope that this works. And it does not. So, I was not in radian mode?
Nope, you're not.
I wasn't?
No, you are not.
Where's mode? Mode?
Down. It's
Down.
down.
Down. Yes.
I can't see it. I was in radian mode. I did? Oh. So, this is good. This is error. Very good. So what I forgot was just a minor thing right here. A variable. Okay? Second. Is this insert?
No.
Yes, it is.
Insert X. Okay. Now I'm going to hit drop. Perfect. Look at that. Okay. So that's a mistake. I made that mistake on purpose because that's a lot. A lot of you guys will make a similar mistake. Now, wait. Hold on. I'm not done yet. So then what they want to know is how high will the tide be? Or how, not tide, how long will the days of the year be on the 91st? What does it say? 91st day. So what you do is you go second table set. Does this say table set? Or does this say table set? Okay. Table set. Make sure you're on ask. Okay. And then if you go second table, okay, and you plug in 91. On the night, no, they want to know on the 91st day of the year, right? Because when 91, and you should get out 12.72 days of sunlight. So that's the way, like a farmer might want to use that, okay? If